Good morning, everyone. Can you hear me today?
Yep.
Okay, great. All right, so let's start with your questions. Please put them on chat. Any questions from the homework? Okay. So we'll look at the problem Chris gave us, and then we move on. So number 10. So in this section, as I said yesterday, it's barely the formula, so you don't really have to derive it. You just have to know how to use it. That's really basically those two sections about. So in number 10, we have the following. Which section, Chris? There's two sections, 6.5 and 6. Number 10 is which section?
Let me look real quick.
Okay. 6.6. Okay, so we have the following. Y equal half EX plus E minus X on the interval minus ln of 2 ln of 2. Okay. Section 6 points. Oh no, sorry, I'm doing 6 point. My apology. 6.6. Okay. I was doing 6.5. So we have the curve y equal x cube and x between 0 and 1 about the x-axis. And the question is, so that's section 6.6, number 10. And the question is, find the surface of revolution. Okay. So basically we have a curve. As I said, you always have to draw those in, and we rotate it. And this is generate a surface. It's like a horn in here. And the question is to find the surface area. All right. So the surface area is basically the formula. We are rotating around the x-axis. So it's equal to integral from 0 to 1, because it's from 0 to 1, of 2 pi times the function, the square root of 1 plus derivative square dx. So it's really a matter of applying it. So now what's the f prime? We have y equal x cube. It means f of x equal x cube. The derivative is 3x squared. So let us write this down. So it's going to give me 2 pi is a constant. Integral from 0 to 1. F, the function is the cubing function. 1 plus f prime is 3x squared dx. So it's going to give me 2 pi times integral from 0 to 1 of x cubed, the square root of 1 plus 3x squared to the power 2, 3x squared times 3x squared is 9x4 dx. And now we have to basically find the antiderivative. So quickly, how shall we find the antiderivative?
Use substitution.
Substitution. And we're done. U equal 1 plus 9x4. And then the derivative is 36 x cubed dx. Since I know I only have x cubed here, so I have 1 over 36 du is x cubed dx. And then I'm going to change limit. So if x is 0, these are the limit. My upper limit is 1. If x is 1, the new upper limit become 1 plus 9, which is equal to 10. And now I'm going to make it totally a new integral, totally new, where the variable is u. So this goes from 1 to 10 of x cubed dx. This is 1 over 36 du. And this is the square root of u. So finally, I will have 2 pi. 36 is a constant. I get it out. Antiderivative of square root of u to the power a half between 1 and 10. And those are constant. I can put them outside the evaluation. And we're done now. This is going to give me pi. 2 and 36 give me 9. That's 27. 10 to the power 3 halves minus 1. And then you basically conclude. Any questions before we proceed to the last one?
You don't have to substitute 1 plus 9x to the 4th?
No, because.
Why don't you?
Tell me why.
I'm not sure. That's what I've been doing. I think that's why I got the problem wrong.
Right, because I changed the limit already. If you don't change the limit.
If you hadn't changed the limit, then you would substitute u in?
Yes, exactly. So either you change the limit, or if you don't change the limit, if you do not change the limit, it means you basically find the antiderivative. It means if you only do that, if you only find the antiderivative, by of course substitution, there is no way out. You forget about the limit, you don't do anything. And then you end up with pi over 27, if you do it correctly, u to the power 3 half. You did not change the limit, you go back to the original variable. Okay, and then the definite integral from 0 to 1 will be equal pi over 27 between 0 and 1. And this will be 1 plus 9x4. Okay, so either you keep x, the limit 0, 1. If you change the limit, then that's it. You forget about x, you become your new variable with the new limit.
Okay, thank you.
Very clear?
Yeah, that's clear.
Crucial, because, you know, I mean, that's, you're going to be dealing with this a lot. Now, part 2 is, now we're going to look at number 11. And let's see what it is about. Okay, so y equal, you have a function, 3x to the power a third, x between 0 and 8 over 3, and it is about the y-axis. Okay, so about the y-axis, yesterday I did not give you the formula for about the y-axis. I only gave you formula about the x-axis, but I'm thinking if the book gave it to you. I don't know, it doesn't seem that the book gave it to you. Anyway, so about the y-axis, actually the formula is basically the same. In other words, this is, here we are. Okay. Suppose x is a function of y. So x is a function of y, okay? And you have the graph here, and you're gonna rotate around the y-axis. Okay, and you get a surface. As I said, that's the lateral surface we're interested in. We're not interested in the volume, this one. That's the surface area. So if we rotate, so let x be, and where y between, I don't know, C and D. And the formula will be exactly the same, but instead of doing things with respect to x, we do them with respect to y. And then rotate about y-axis. And then the surface area would be the integral from C to D of 2 pi g of y, the square root of 1 plus g prime. So now we look at dy. Okay. So if x is a function of y, or basically if we rotate about the y-axis, that's how we have to use this formula we have to use. So instead of x doing everything with respect to x, we do it with respect to y. So in this problem, what is the situation? So first, we want to rewrite it as x as a function of y because we're about the y-axis. You write x as function of y. It means solve for x as a function of y. So we'll have y cubed, we raise both to the power 3 equal 3x. X is 1 over 3 y to the power 3. So again, we have, so this is my function. If we graph it, actually we get this graph. And this is 8 over 3. And you're going to rotate around the y-axis. Right? So step number 1, we have to write x as a function of y. So this is y equal 3x to the power a third, means x is 1 over 3 y cubed. Now step 2, we have to find the limit in terms of y, because the formula tells you it has to be what are the limit. How can we cover the region, basically, if y is the variable? So what is the value here? If x is a third, so suppose x is 8 over 3, then my y is, I plug in for y, 3 times 8 over 3, it's in 8, which is equal to 3. And then the formula will become, so now this is my g of y if you want, is 1/3 y to the power 3. So the derivative, now everything is in terms of y, will become y squared. And the surface area will become 2y pi integral from 0 to 3 of g of y square root of 1 plus the derivative squared dy. So to find the surface area, if we are rotating about the y-axis, and then we have to express x as a function of y, find also the limit in terms of y, and then use the same formula exactly verbatim the same. So it's going to give me 2 pi integral, so 2 pi over 3 basically, from 0 to 3 of y to the power 3, 1 plus y to the 4 dy. And then finally, we say again a substitution. We put u to be 1 plus y to the power 4, the du is 1/4 y cubed. And then the limit, y0, u is 1, y3, u is 1 plus 3 to the power 4, that's going to give me 81, will give me 82. And then this will become. Now I changed my limit. I have a whole new integral in u. I don't worry about y anymore. No, we have y cubed dy. So y cubed dy is going to be 4 du. Am I goofing a lot? You guys are not correcting me. Okay. So y cubed dy, that's going to give me 1 over 4 du times the square root of u. Okay. And the rest is what I did a minute ago. So the rest is exactly what I did a minute ago. So what did I do the minute ago? I have to take the 4 out. And then find the antiderivative. I mean, not all of them is the square root of u, but the square root of 2 shows up a lot, between 1 and 82. Multiply. So finally, I will get 4 over 4. That's cancel out. I'll have pi over 9. And then I will have 82 to the power 3/2 minus 1. Okay, so if we're rotating about the y-axis, the formula is very much the same, but we have to express x as a function of y and then proceed. So the one we saw yesterday was rotation about the x-axis, but this problem is about the y-axis.
I have a question real quick.
Of course, go ahead.
For when you changed it to y, how did you get the upper limit to be 3?
Okay, let's go back. According to them, x is between 0 and 1/3.
Okay.
Okay. So because y now is my variable, I have to see y vary from where to where. With me so far?
Mm-hmm.
So if x is 8 over 3, what is the y? It means I want this point on the graph.
So you just plug it back into the equation.
Yeah, this one, because I have the x. All right. So if x is 8 over 3, y will be 3 times 8 over 3, which is in 8 to the power 1/3, right?
Okay. So it'd be 2?
It will be 2, of course.
Okay.
So it will be 2. You guys are not awake. 2, 2, 17. 17, 17, and 17.
Okay.
Thanks a lot, Luke. Anything else? No, sorry, it's not Luke. Thanks a lot, whoever is asking the question. Okay, anything else? All right. So today we're going to move on to section 6.7. It's physical application. Basically, we will do one application to that, which is the notion of work. So section 6.7. Okay, we will do work. Now, part of the work will be done before the exam. Actually, I will do the easy part before the exam. And the hardest part, I will do it after the exam. So you won't have a hard part for this first exam. Okay, so work. First, what is work? Let us remember in physics. So the word work have a very specific meaning in physics. So what is work in physics? Anybody remember? Basically, it involves an object which is moving. Okay, in physics, work talk about an object moving. And what was the definition of work? Anybody has any recollection?
Isn't it force times displacement?
Right, it's the force times the displacement, exactly. So what's the definition in work? So you have an object, basically you have to imagine you have an object like a book, for example, and you are moving this book. There is motion, you are moving it, you are lifting it. So work in physics is nothing more than the force you need to move the object times how long you move it, the distance. So let us define this in a more accurate way. So according to physics, okay, so that's a very technical definition. So according to physics, when a constant force, and of course I underlined the word constant, when a constant force F is applied to move an object, a distance d in the direction of the force. So when I say in the direction of the force, it means if you're moving the object, up, it means the force is vertical, but then the force is in the direction of the way we're moving. The case we're not considering in this course is something like that. Suppose you have like a stone and you're moving it on a slanted line. The force here is vertical because it's due to gravity, but the motion is not in the direction of the force because the motion is this way. This is not the case we consider in this class. We only consider the cases when the force and the direction of the motion are along the same line. So this is not the case. You will see that in physics and you will see that in calculus 3. And we're only considering up and down basically motion and left and right. So according to physics, when a constant force F is applied to move an object, a distance d in the direction of the force, then the work is defined as the force times the distance. So work is force times the distance. So that's how we define work in physics. So to be work, there should be an object moving. Without object, a certain distance. If the object is not moving, we really don't talk about work because it's force times distance. Now, the unit of work. So the unit of work, we have two major units of work. First, depending on the unit we use for the force and the distance. So if force is measured, if the force is measured in pound and distance in foot or feet, then the unit of the force of work is foot-pound. So the unit change. So if the force is measured in pound and distance in feet, that's the unit of force is foot-pound. However, if the force is measured in Newton, so that's another unit of force. It's measured in Newton. And the distance in meters, which is the unit of measurement, as I said, in everywhere else in the world, except here in the States, because foot and pound are only used here. So its force is measured in Newton and distance in meters, then the unit of work is Newton meter, or, and probably a lot of you are familiar with it, what's the other name for it? You guys remember? No? Seen it?
Joule.
Joule. Okay, so this is the unit of work. All right, so it depends what you use for force and distance, foot pound, or sorry, I think pound foot, or it is joule if this force is in Newton and the distance is in meters. So this is the unit that we use for work. So like a very, very straightforward example, nothing deep. Can I move on? Okay. So straightforward example. Suppose Suppose find the work required. So find the work required to lift a 3-pound stone 5 feet above ground. Okay, so find the work required to lift a 3-pound stone 5 feet above ground. So here we have a stone and it weighs 3 pounds. And we need to lift it 5 feet. Now, as probably you know, the force you need to lift the stone is exactly equal to its weight, because you have definitely to compensate for the force due to gravity. So when you want to push it, the force you need to push it is exactly the weight of the stone. So the force needed, that's just a constant force, is 3 pounds, the weight of the stone. So the work is going to be the force you need times the distance. It's 15 foot-pound. Okay, so that's a very simplest, that's the simplest possible scenario. So we have a fixed force that we are lifting, and that's the work. Now it's more common. If you take a stone, 3 pounds, and you carry it, you don't move it, you carry it for a long time. I mean, you carry it for 5 hours. What's the work? Simple question. You take the stone, you hold it in your hand, you don't move, you just carry it for a long, long time. What's the
No
work
work.
you do? What?
No work.
No work. The work is zero. Work involves movement. If you move the object, you're doing work. It's not how tired you are. If you move the object, you do work. If you don't move the object, the work is absolutely zero. So there should be a motion to talk about work. Without it, there is no work. All right, so it's very simple. The problem is very simple. As long as the force you need to move the object is constant, you're not changing the force. So most of the time, this doesn't happen. And that's where calculus gets into the picture. A lot of time when you are moving an object or you're moving something, the force vary. And the question is, as the force vary, what's the work? How are we going to define work? So example of force varying. One example that is very students understand very easy is what I call the leaking bucket. So if you have a bucket full of water, if you want, or sand, and the bucket leaks, all right? So as you're moving it up, okay, it's leaking, so it's losing sand. So as you move it up, of course, the weight is going to get less and less. So the force to move it is going to get less and less. So the force is a variable. So since the force is a variable, so the question is, what's work in this case? How are we going to define work? Because the force vary. What do we mean by work? The work is force times distance as long as the force is constant. But now the work, so as we go up, we're doing the weight getting less and less and less. So what's the work in this case when the force is varying? The other important problem that we will take and we will do in details, hopefully today, is the following. The spring problem. What's the spring? So suppose you have a spring. That's the spring. And that's its equilibrium position. Okay? And then you take the spring by the mass at the end of it, and you start moving the spring. And the question is, the force, does the force vary? The force you need to move the spring by, does it vary? Yes or no?
Yeah.
Listening. Is the force varying? So imagine the spring and you're pulling the spring. You're pulling it and pulling it and pulling it. Does the force vary?
Yes.
Yes. The more you pull, is it less force or more force to pull it further?
More.
more, because you have to restore the spring is going to fight more and take you back. So the more you push, the more you push, the force you need to push it more is going to increase because you are fighting the spring. There is the restoring force of the spring that's going to move the spring back. So the more you push, the more force you need to keep pushing forward and forward and forward. So the force is also variable. Okay, so those are two examples of cases where the force you need is actually changing. So the question is, what is the definition of work in this scenario? So as the force changes, what force, what work will be? Okay, so that's really what our concern in this section. Calculus is about things that changes and how to deal with it. So how we are going to deal with this problem? So if you have an object and this object is moving from A to B, but as you move, the force needed is actually changing. That's really my problem. And the question is, what's the work? All right, so let me set up the problem and then start thinking about how we're going to solve work in this case. So my problem is the following. Variable force. That's really what we're going to talk about. Variable force. So suppose a force. I put f of x because I want to say that it changes with x. Suppose a force moves an object in a positive direction along the x-axis. So I have a force from a point A to a point B. Question is, find the work done by the force. So the force is moving the object, but the force changes with the position of the object. And the question is, what's the work? So that's really my picture here. So that's my picture. Okay, that's point A. That's the x-axis. Let me suppose this here. And that's B. That's the y-axis, sorry, from A to B. And I have a force, so that's an object. And this is at the point X. And f of x is the following, the force needed. So f of x is the force needed to move the object at the point X. It means when the object is here, we need a force, that f of x, force needed to move the object at the point X. And the force changes with the position. Move the object at the point X. Okay. And what is the force? All right. We will solve this problem like we always solve those calculus problem when things vary. So the idea is, since the force change, we're going to break the problem into pieces. So we're going to divide into chunk, cut into pieces the following way. So we divide the interval AB into little subinterval, equal subintervals of length delta x each. Okay. So we draw the picture one more time. Okay, that's my A, that's my B. I'm going to divide this into pieces, etc. So at some point, I'm going to call this, let us say, xi plus 1, and this is xi. Okay. Now, how we are going to think? We're going to think along the same line. So this is x1, for example, x2. Okay, let me tell you the strategy and then we proceed. The force is changing, and we know that. It means the force you need to move the object, when the object is initially at A, the force we needed to move it when it is here is different than the force we need to move it when we are at xi. So we need it all, imagine the spring. If the spring here, the force to move it is changing. So we have an issue. So what we're going to do is we're going to divide it into pieces. And then I'm going to compute the work to go from here to here. This little distance. How much work we need. Then I'm going to compute the work to go from here to here. Then I'm going to add to it the work to go from here to here. So then I'm going to keep going and add this work. So how much work we need, plus how much, plus how much, plus how much. So we're going to divide it into a little small task, the problem. So I'm going to call Wi to be. Sometimes this is called element of work. Element of work in a lot of physics book. All right. So we're going to call Wi the work needed to move the object. The object from xi to xi plus 1. Okay, so W0 to move it from here to here, W1 to move it from here to here. Now, what's the work needed to move the object from xi to xi plus 1? So my object is here. I want to move it all the way here. I'm going to move, and I'm going to move it a very small distance. So from here to here, this is delta x. And I'm going to move it very little, very tiny. So we're going to make the following assumption, which is, makes sense. I only can compute work if the force is constant. If the force is not constant, I have an issue. So what I'm going to assume is the following. That's my main assumption. If delta x is small, which delta x is going to be small, we're going to assume that the force needed to move the object from here to here is actually not changing. Because if delta x is small, I can make this assumption. So if delta x is very small, we assume that the force, that's going to be our main assumption. We assume that the force is not changing. It means it's constant. We assume that the force is constant on the interval xi plus 1. If delta x, so I'm moving this, imagine anything. I'm moving this little thing, this object from here to here. When the object is here, I need a certain force, f of xi, to move it. When it's here, my force is changing. But if delta x is very, very small, I can assume that on this interval, the force is not really changing, and its value remain the value when the object was at xi. Its value is f of xi. That's going to be the heart of what we are doing. So we're going to assume that when delta x is small, the force is not changing on this little interval. So from here to here, imagine the following scenario. The constant force is whatever force I needed to move it from A to x1. It remained the same. When I hit here, the force I need is whatever force I need when the object was at x1. So we're going to assume this to be able to go back to the scenario when the force is constant. So the work needed, so Wi, to move from xi is going to become the force at xi times the little delta x. That's going to be Wi. So now the total work is going to be, so the total work is going to be almost equal to the work to go from here to here. I'm going to call this W0 plus W1 plus Wi. So the little bit of work, the contribution of each one of them. So remember, W0 for me is work to move from x0 to x1. So that's work to move from x0 to x1. That's W0. This is from x1 to x2, the work. This from xi to xi plus 1, and this is from xin minus 1 to xi. So I computed, added a little bit of work for each one. So this is going to be equal to, and this is where my Riemann sum will famously come. It's going to be equal to, so the work going to be equal to sigma of those little work done on every piece by itself. It means the sum of f of xi delta x. 0 to n minus 1. Again, we always go after a Riemann sum. And the way we went after it here is we added the contribution of work. So the contribution of the work from here to here, plus from here to here, plus from here to here, plus from here to here. So we can assume the force is constant and use what we need. So the total work now, we go to a Riemann sum. The smaller delta x, the better our assumption. The smaller delta x, the better our assumption. It's going to be integral, adding integral of f of x dx, and the integral goes from a to b, the interval we divided. Okay, so that's really how we are going to define work. So let us sum up this into a big formula. Okay, so definition of work. I'm going to just rewrite the formula neatly. Definition. The work done by a variable force f of x moving an object along a line from x equal a to x equal to b in the direction of the force is going to be integral from a to b of f of x dx. Whatever this variable force is going to be that. And the picture for you should be, this is a, this is b. At x, the force, once the object is in this position, f of x is the force needed to keep pushing it. And the line could be horizontal or vertical. It actually does not really matter in the picture at all. Okay. The first straightforward example, and then we start talking about the problem of spring in a more detail. So the first straightforward example, just to see how to apply this formula. So I'm just slowing down a little bit. How much work is needed to move an object from x equals 0 to x equal to 3? So this is my line. This is 0 and the 3. And meter is the unit here. I want to move it from here to here. But the force I need to move it vary with where the object is. So we have this object and we are moving it. But the force changes with where the object is on the line. So if the object is at the point X, and this is my object, the force we needed is really increasing, is 2 times x squared. Because the force is needed. So for example, how do you understand that? So f of 1, for example, f of 1 is 2 times 1 squared, which is 2 Newton, which means to you that, I mean, you don't have to write everything. If the object is 1 meter away from 0, the object is here, and you want to push it, you need 2 Newton force to push it. That's really what this force needs. So f of 2, so the force is increasing, is 2, according to the formula, 2 times the distance squared, which is 8. It means if the object is here, that's the same object, and you want to move it, the force you need is 8 Newton. That's really how we understand, and we go on, and so on and so forth. So here you need 2 Newton to move it. Here you need 8 Newton to move it. If you are halfway, you need somewhere between 2 and 8. So everywhere the object is, you need a different force to keep moving. And the question, what is the work? So in this scenario, the work is given by the simple formula. It's the force dx. This is basically, that's the idea of delta x. That's the idea of splitting it. The dx represent the little bit that we move, and this represent the force we needed to move it a little bit. And the integral goes from where? From 0 all the way to 3. So a very straightforward application. So this is going to be equal to 2/3 x cubed between 0 and 3, and 2/3 27 minus 0, so which is going to be equal to 2 times 9, 18 joule in this case, because my unit are meter and Newton, which give me joule. All right, so that's a typical application.
I have a question.
Yes, please go ahead.
What did you do to the right with like the line right there? Yes, this part.
Yeah, what's your question?
I'm confused on how you got the 2 newtons and how you got the 8.
Yeah. Okay. The idea is understand what this f of x means. So they are telling you that the force is 2x squared. Okay. And the goal is, what does this mean to you? What does this mean to you? It means the following. I'm moving an object from 0 to 3. I mean, imagine you're moving this object. But the force changes with where my object is. Okay, so suppose my object is 1 unit away. What does this formula tells me? Tells me that if x is 1, then the force is 2 times 1 square, which is equal to 2 Newton. It means when the object is here, so you have an object that you are moving. When it is here, the force to move it forward is 2 Newton. Now, if the object is here, this formula tells you that the force you need, you plug in 2 for x, is 2 times 4, 8 Newton. So the force is actually changing. So this is a huge force to move the object. Okay, so the force you need to keep moving it is actually changing with the position of the object. That's what I'm getting. That's how you understand this formula right there. So the force is not really constant. It's an object that something is happening to it as you are moving it. And the force to move it is actually increasing. That's where the numbers are coming from.
All right, okay, that makes sense.
Is it making better sense?
Yes.
Okay, it doesn't have to do anything work, you just apply the formula, but to understand this function, what this is telling us, that's really what it's really telling me. So it's an object where the force to move it is changing. Understanding, okay, what is the force? So if it's here at 1 unit, you need 2 Newton to basically move this object, of course. That's what's telling me. Once it's here, you need 8 Newton to move it, and so on and so forth. Now, the application that we will do in this course for this, one application, is spring. So I'll talk a little bit about spring, and tomorrow we will take over. So spring. So as I said, the work spring is a variable force. So work done on a spring. So this is a spring. That's the picture we're going to have. Because spring are easy objects. That's my spring. Okay. And imagine pulling the spring. We are actually pulling the spring. Okay. And the force, when you pull the spring, is a variable force. The force to pull it is a variable force. So to be able to find the work, okay, we need a formula for the force. So what is the formula that we have for the force? So we're going to talk about something called Hooke's law. Okay, Hooke's law. So the x, yes, exactly, yeah. The unit on the x-axis is whatever is given to you as a unit. Hooke's law tells me that. Hooke's law states that suppose you have a spring, then the force required. So we have a spring. The force required to maintain a spring stretched x unit beyond its natural length is given by f of x equal k, a constant, times x, where k is a positive constant called the spring constant, and x of x equal to x, k is called x is basically the amount of stretching. Or compressing in general. Okay, so what do we mean by that? The idea is the following. So I draw my spring again. That's the spring. And that's my spring. And always the natural position of the spring, that's 0, sorry. Zero is always the equilibrium position of the spring. Okay, so on the x-axis, we always put the equilibrium, we put 0 is at the equilibrium position. And I take the spring and I stretch it. I stretch it a little bit. The more I stretch, the more force I need. And what this is going to tell me, suppose I take it and I stretch it up to here. This is my x. Hooke's law tells me that the force here, we need it, is always a certain constant k times the amount of stretching, where k depends on the stiffness of the spring. The stiffer the spring, the higher the spring constant is. So this is actually giving me only the general formula for the force. So the force needed is always proportional to the amount of stretching. The more you stretch, the more force you need. And Hooke's law tells me it's k times x. It means it's not k times x squared. It's proportional to the amount of stretching. So how can we use this formula to be able to find the force acting on a spring, and then tomorrow we do the work. So for example, very simple. Suppose I tell you the following example. Suppose, for example, okay, suppose it takes.
Professor, is it okay if I leave? I have a different class.
Oh, sure. And everybody can leave to a different class. I can take you there from tomorrow. All right. So that's the idea of a spring. What we're going to do tomorrow is basically we're going to find the work done on the spring. So this is the formula for it. And tomorrow we're going to spend the whole hour working with this formula. So I will definitely stop right there. Anybody has any questions? Did you guys start doing the review? Anybody?
Yes.
Okay, please get started. Don't wait for the last minute. And on Thursday, I will review with you. So tomorrow we're gonna work on the spring, and Thursday I will review with you. Okay? All right,
Have a good day.
bye-bye.
Goodbye. Thank you.
Bye-bye.